Okay, thanks very much. Very nice to be here in Sheffield. I actually lived and worked in Sheffield for a year when I did my year out working for the City Council many years ago. So it's a city I very much do like coming back to. So I've been asked to talk to you about Passivhaus, introduce it to you. I'm sure there's a whole range of knowledge of Passivhaus, but I just wanted to start off by just showing you a few examples of the type of work that we've done as architects over the years. So this was a primary school that we did many years ago, which was actually the first BREEAM Excellent primary school in the UK at the time. And as you can see from these photographs, we're passionate about creating really good internal environments in our buildings that are full of light and daylight and good ventilation, healthy natural materials. This is a cycle centre in the Snowdonia National Forest, which was built entirely out of local Welsh timber from the forest around the building. This was a community leisure sports and training centre in Wolverhampton, and so this is the badminton hall stroke event space, again bringing good daylight and good material into the type of space that's often very cold and clinical in a sort of sports building. We also do quite a lot of housing. This was the UK's first co-housing scheme, new build scheme in Stroud, where we worked with 35 families who became the developers who bought and developed the site and created a uniquely community-based sustainable housing scheme. This is a recently finished school in London. So just there's a few examples, and as Christian just mentioned, we see our purpose as designing life-enhancing, genuinely sustainable architecture. So what do I mean by genuinely sustainable? Well, I think one of the biggest scandals in the building industry is the performance gap, the gap that exists between the amount of energy that buildings use in reality compared to how much theoretically they should when they designed. And this gap can be huge by factors of 3, 4, 5 times. And you can imagine if you bought a car that claimed to do 50 miles to the gallon, and however well or badly you drove it, it did less than 10, you would be staggered and you would take your car back. But that's the reality of what happens in buildings. And the other thing that I think the UK building industry or the whole policy framework in the UK has latched onto is just simply adding gadgets to buildings, turbines and PVs and wood pellet boilers and things. Now, I'm not against renewables, but I'm against them when they're used as an excuse for efficiency in buildings. So the B&Q wind turbine, when it was launched a few years ago, claimed to provide, I think, 70% of households, or offset 70% of a household's energy needs. Now, in the Warwick wind trials, they actually transpired to only produce equivalent of 2.4%. So I worked out you'd need 42 of them on your house, which is obviously completely stupid. But even if you did that, it would still be daft because the house would still be using a load of energy and you're just offsetting it. It's much better to use less energy. I always liken energy to rubbish. We all know it's good to recycle rubbish, but it's also much better just to create less rubbish in the first place. So renewable energy is good, but it's much better, first of all, to use less energy and then look at what you can generate from a renewable source. The other big scandal in the industry in terms of the performance gap is the fact that many buildings not only don't or use too much energy, they're really uncomfortable. They don't perform in terms of the environment that we're trying to create. And I think many clients of new buildings feel like the crash test dummy of the auto industry. They actually feel like they're being tested out in the building and the building's failing around them and the environment is not as good as it should be. So for us, we're trying to address the performance gap in energy, but also the performance gap in terms of the comfort and what it's like for people to be in the buildings. So at Architype, as Fionn knows from work that we collaborated together many years ago at Oxford Brookes, we're passionate about building performance, actually monitoring buildings and find out how they work, why they don't work, how they could work better, and then to learn those lessons and apply them back into the design of future buildings. And in the work that we did with Jon and Oxford Brookes, we discovered many things about our own buildings that didn't work as well as they should do. And this was really a sort of awakening for us, and we started to think about how we could make our buildings work better. And this is one of the reasons why we started exploring Passivhaus and then started doing Passivhaus, and now have, over many, many years, also monitored our Passivhaus projects. So I'm going to talk you through now some different aspects about Passivhaus. What is it? Why might we do it? And how do we do it? So first of all, what is Passivhaus? Well, I think everybody knows, I'm sure, that it's a rigorous energy standard. It's about saving energy. But I think the other thing that is really important about it is to understand it's also about comfort. It's about creating really good internal comfort in the buildings for the least possible energy. So it's energy and it's comfort. But there's two other aspects of it which I think are really important. First of all, like I described our approach to monitoring buildings, it's based on the evidence of how buildings actually work in reality, and the standard is designed around building physics and the evidence of how buildings actually work. And it's also a quality assurance standard. To actually get Passivhaus certification, you have to demonstrate and prove that your design meets the standard of Passivhaus, and you have to demonstrate and prove that your construction process and standards achieve that. And our experience of doing it is that it's very, very rigorous. And because it's rigorous and because it's based on evidence, our experience of Passivhaus ourselves and the evidence of others across Europe over the last 25 plus years is that it really does work in terms of comfort and in terms of energy performance. So what is Passivhaus? Well, this is just a simple illustration of two ways of keeping coffee warm. One, on the right-hand side, the classic filter machine, which requires a constant supply of energy in an attempt to keep the coffee warm enough to drink. The thermos, on the other hand, once the coffee's in there hot, stays hot for many, many hours. The other thing about the filter coffee and its constant supply of heat to actually keep it warm is that by the time you come to drink it a few hours later, it tastes disgusting as well. And that's my illustration of the comfort side. And if you take a thermal imaging picture of that, you can see just how much energy is escaping through the constant supply of energy into that coffee. So just in terms of the technical, what is Passivhaus? Well, it actually creates an absolute limit on energy per square metre of the building per year for heating, which is 15 kilowatts. That's a bit like miles to the gallon. It sets an overall primary energy limit for all energy used in the building, multiplied by a factor for its efficiency of supply. It sets an absolute limit of 5% of occupied hours cannot go above 25 degrees centigrade, so that's partly about the comfort. It requires buildings to be tested to air tightness of 0.6, and if you think building regs is 10, it's a drastic improvement in the air tightness. It requires you to eliminate thermal bridges, which are bits of the building, the structure that leak heat to the outside through the insulation. You need better U values in the fabric. You need triple glazed windows of a very high standard. And you need mechanical ventilation with heat recovery, MVHR, to ensure sufficient good quality ventilation when you particularly need it in winter, whilst avoiding the loss of heat through ventilation through trickle or opening windows. You can, of course, still open the windows, and people do, especially in summer, but it guarantees a constant supply of fresh air into the building without the loss of heat that you'd get otherwise. So it's about orientation and form, getting the building facing the right direction to control and optimize and limit solar gain so that it works well. Better fabric, as I've said. It's about using also the PHPP, the Passivhaus Planning Package, to model and optimize the design to actually enable you through design. I would see PHPP as a design tool as well as a compliance prover. Now, the one thing that Passivhaus doesn't do is it doesn't dictate the type of construction. You can build using any type of construction you want. It just sets the standards that you have to achieve through that construction. So this is a little diagram, just illustrates Passivhaus. You can see there draft-free construction with continuous air barrier, sunlight in the winter getting into half the building to warm it up, shading out so it doesn't overheat it in summer, heat recovery unit, just very, very simple. It's not rocket science, it's not high technology, it's simple, basic, good quality design and construction. So why might we do Passivhaus? Well, first of all, as I indicated earlier on, I think that saving energy by good design and good construction is more logical than using energy that you don't need to be using and then just simply offsetting it with renewables. We're never going to become carbon neutral if we constantly use too much and try and offset it. We need to use less in everything that we do. I also think that getting the basics of good low energy design right is more effective than simply ticking boxes that you do with BREEAM or adding eco-bling to buildings just for the sake of making them look green. And I also think that in the time of financial austerity and environmental challenge that we're in ever more than ever, it's actually a more economic solution because it offers affordable construction and low running costs over the lifetime of the building. So it's actually, we often, when we're talking to clients, we're not selling Passivhaus as some worthy green thing. We're selling it as good economic common sense. And this is just some example of monitoring done in Germany of 3 different housing schemes, 1 low energy and 3 Passivhaus schemes. Each little bar is energy consumption in an individual house. So you can see that how people live and use the house does affect, of course, how much energy each house uses. But the average on the 3 Passivhaus schemes, 13 and 14 kilowatt hours. The average on the German low energy scheme, which is better than a typical UK scheme, obviously, is 66. Even the very, very worst performing Passivhaus that must have his windows open and the heating on all the time is still about the same as the very, very best in the low energy scheme. And some of them are getting right down to negligible, completely, almost hardly any energy whatsoever. So this is, it really, really does work. So in terms of Architype's Passivhaus projects, we did the first Passivhaus schools in the UK and have gone on doing several since. A Passivhaus archive building, a Passivhaus university building at the University of East Anglia, a number of one-off Passivhaus houses. We're doing extra care currently, older people's accommodation for Exeter City Council, social housing for various councils, and we've also established our own development company to do large-scale private housing development. So currently, I think when we last checked, as we monitor, about 65% of all the projects in the office now are being designed to Passivhaus. So just a few examples of that. This was the Hereford Archive and Records Centre, which was the first archive building built to Passivhaus. So this not only required the part of the building where people occupy it to be to a good environmental standard, but we had to provide very, very tight environmental conditions for the storage of very, very sensitive archive materials. And Passivhaus seemed the logical way to do that. So we have 2 parts of the building. The archive store, which you can see on the left here, it's a concrete structure clad with cedar shingles. And then on the right-hand side, we've got a timber frame building clad in render. Very high levels of insulation. That's inside part of the public part of the building. Now, we looked at a number of precedents for archive buildings, and one particular one, which was typical for the same size building, was actually consuming over about £64,000 worth a year of energy. And we predicted by designing the Hereford building to Passivhaus, it would come in at around about 11 or 12,000, so a massive reduction in energy. That was predicted. In the first year of its occupation, this is what it actually consumed. Absolutely spot on. Slightly more thermal, slightly less electricity, but let's say negligible, but overall total exactly spot on. And then in terms of the environmental conditions of temperature and humidity that we have to maintain for these precious archives, there you've got temperature. This is the most boring graph in the world that I'm going to show you because it's showing such constant temperature and such constant humidity, which is exactly what you need for storage of precious archives. And that building at that point had no heating in it from February since last spring. This is an example of one of the schools, Wilkinson Primary School in Wolverhampton, which I hope I'm also demonstrating that by designing Passivhaus, it doesn't change at all the design quality and the approach to creating good architecture that we're passionate about. So I would absolutely say, I think lots of architects fear Passivhaus as restricting their design. It does influence how you design, but it still gives you, I think, plenty of space to create great buildings. This is the building that we finished last year for the University of East Anglia. Here it was a really demanding brief of not only Passivhaus, but also natural materials and BREEAM outstanding. So we've got a whole palette of fascinating materials on this building, including, as you can see on the left-hand wing or on the outside of the building, it's clad with thatch obtained from local Norfolk thatched by the master thatcher of Norfolk and his team. So you couldn't get much more local than that. And then inside, a whole range of different materials, including a lot of timber from the local Thetford forest. This is the extra care scheme we're currently doing for Exeter City Council, 53 flats for older people, built not only to Passivhaus but to the German building biology standard, which sets very, very high standards for the quality of the internal air and the materials that you use. This is a scheme designed by another architect, Rick Mather, to Passivhaus. Theoretically, we then became the delivery architect with the contractor. Actually, we called it our retrofit new build because we had to do so much from the original design to actually make it work to Passivhaus because it hadn't fully been thought through. But it's a very successful scheme at the end of the day. And we're currently working on Agar Grove, which is a big development for London Borough of Camden, where all the buildings there for both sale and for social housing is being done to Passivhaus. And we're currently designing a secondary school in London, which will be the first Passivhaus secondary school in the UK. And this is the scheme that we're doing with our own development company that we set up to do a development of 150 Passivhaus houses on a site in rural Herefordshire, where we've tried to create a more rural approach to high quality design as well as Passivhaus compared to the usual developer housing that goes on around Herefordshire. And here are some of the school projects that we're currently doing and have got ongoing. So how do you do Passivhaus? Well, a number of basic rules, apart from all the key things I've mentioned earlier, that help make Passivhaus affordable and economic. First of all, simplicity of form. I think it's kind of obvious when you look at it, but if you could actually think, if you think about the useful floor area of a building and the total surface area of it, that has a very, very direct impact on the efficiency of it. So this diagram here shows a number of different buildings, from ones at the top right-hand corner, which have 3 or 4 times the surface area compared to the useful internal area, down to ones at the bottom, where it's a ratio of more 1-to-1. And if you think you're creating a building that could have as much as 3 or 4 times as much surface area, that's 3 or 4 times as much envelope to insulate, and because you've got more heat loss, you need to insulate it to a higher level of thickness. So it's a double whammy. So think about the efficiency of the shape is a key thing. So I don't know who designed this, but it's a primary school that I found somewhere. Complicated, fiddly shape means that you're always going to struggle to make it perform in terms of efficiency. So when we designed our first schools, we looked at creating a more compact form, 2-storey, but still within that creating some very, very dynamic spaces. So creating the overall form as a simpler form doesn't mean that the building becomes boring. You can still create really wonderful spaces within that and dynamic teaching spaces. This was the other school we did at the time. Again, a more compact 2-storey plan, a simple section, but creating some really exciting spaces within that. Then simplicity of detailing. I think architects and engineers, we all love complexity. We like making things more complicated. The more complicated you make the detailing, the harder it will be to be thermally efficient and airtight. So if you look at the foundation, most foundations have concrete going right down into the ground, and that is constantly draining heat into the ground. What we do on Passivhaus buildings instead is basically create the building sitting on a floating concrete raft which sits on insulation. So there's no contact between the ground, the concrete and the ground. And when you do the thermal modelling, you can see how well that keeps the heat in the building, whereas the traditional foundation will see all that heat pouring away into the ground. And we also need to look at getting rid of thermal bridges. So on this building, bits of structure, here in this case steel, going from the inside to the outside, which is just like creating a radiator from the inside to the outside, putting heat into the atmosphere. So instead, we look at creating roof overhangs outside the thermal envelope, for example. Looking very carefully at where the airtightness line runs around the details so that when the builder comes to do it, it's actually doable rather than impossible, as it can be if you don't really think about it. Looking very carefully at the ratios of light and ventilation, and simple strategies as we've got here for natural ventilation, where you can open a big door with louvers on it, which creates a huge amount of fresh air coming into the building without the danger of people falling out or people breaking in. Then simplicity of M&E strategy. When we designed, as an example, the Hereford Archive building, we actually worked out that we could heat the building sufficiently with this. And that would have been a really, really nice, simple M&E strategy. Now, the M&E consultants had a slightly different idea in their mind. They were thinking something more like this. And so we have a constant struggle with engineers to encourage them to think what they can take out, the stuff you don't need to make a building work better. So we're always looking at how we can optimize routes for ductwork to make the ventilation efficient. We're looking at what we can take out. So on our first passive house buildings, even though we proved that we only needed one small domestic boiler, the M&E engineers insisted on putting two in case one failed. Now actually, unbeknown to anybody, both failed when it was cold and snowy, as you can see in the bottom picture. An alarm was triggered at County Hall. It took them a week to get out. When they walked in, it was toasty warm, and they said, well, the alarm must have gone wrong. They went in there, and sure enough, the boilers weren't working. And it was because the backup was really the fact it was a well-insulated building full of warm children. And it was fine. So in the next building, we managed to get away with persuading them to put in one boiler. So that's a large domestic boiler heating a 2,500 square metre primary school. And the reason that works so well is that this is our heat source, kiddie-watts. Children generate heat all the time, to the extent that the radiators that we did provide are now being used as display boards by the teachers, you can see. So they're hardly ever on. But even so, engineers still try to put back in things to make them complicated. And the one thing we learned from our monitoring of buildings is the more complicated you allow an engineer to make things, the less likely it is to work. The more complicated you allow the controls engineers to make the control systems, the less likely it is to work. So after years and years of post-occupancy monitoring and lots of deep design thinking and looking at different options, a way to deal with things like lighting, we came up with a remarkable new innovation to control lighting. There is nothing better than a switch that keeps the lighting simple. As soon as you try and automate it, it won't work. So we're always looking in our work with Passivhaus to look at how you can make everything as simple as possible. So doesn't Passivhaus, we're talking about all these higher standards, cost more? Well, I'm going to introduce you in a minute to, well, first of all, everyone says Passivhaus costs more. It's 5 or 15% more. But how much does construction really cost? So I'm going to introduce you to the Jonathan Hines rule of cost estimating. I don't know if there's any quantifiers in the building. Apologies if there are. But my rule of cost estimating is that if you think it costs more, it will. So if you set off on a project thinking that Passivhaus is going to cost you 10% more, then everyone readjusts that new budget and it will cost more. Price at the end of the day is simply a matter of priority. So if you know you've got a budget which is fixed at this price, then you prioritise everything to make it work for that budget. And if one of your priorities is Passivhaus or natural materials, then you will achieve that. It just means that as an architect, you can't spend money on lots of complicated shapes or funny cladding materials or highly flashy kitchen units. You just need to look at what your priorities are. And our experience is you can always do a very high level of sustainability and achieve Passivhaus at very, very similar or even less cost. So there are things that cost more. You've got more insulation, high performance windows, MVHR, better air tightness. There are some things which save you money. You've got smaller heating systems. In schools, you can get rid of underfloor heating because you don't need it. You have simpler controls and you need less renewables. And there are other things which don't cost anything. If you've just designed a building well, you've designed out thermal bridges, and you've kept the construction simple, that doesn't cost anything. Might even save you a bit more. So these are just figures. When we did our first schools in Wolverhampton, the budget that they had was 1850 square metre, and we delivered both schools for less than that because they said we had to. Then they came back with a reduced budget and still wanted Passivhaus, so we managed to deliver it for less than that. The Hereford Archive building, typical archive buildings around the country, are £2,800 a square metre. We tested the archive building to BREEAM Very Good, and it was 2,040, and then we tested it to Passivhaus, and it was 4.5% cheaper because we needed less M&E kit to actually make the building work. So Passivhaus doesn't need to cost more, it could even cost less. And the other great thing about it is you have a massive reduction in lifecycle costs. So this was analysis of a whole series of school projects looking at lifecycle planned maintenance energy costs compared to BREEAM, and finding differences, particularly on the energy side, of 55%. And over a 25-year design life, at 5% fuel inflation, that's £275,000, or 60 years at 5%, £2 million, huge amounts. On one of our schools, the head teacher, Passivhaus School's head teacher, came from another new school in a neighbouring authority built to building regs by the same contractor into our Passivhaus building in the neighbouring authority. And at her first governance meeting, she questioned the figures that were put in the financial report on energy, because they were £5,000 a year. At a previous school, they'd been £45,000. And that was the difference between the two. So how does it work in terms of monitoring? Well, we undertook a study, a 12-month study, looking at the performance of energy in the schools, but environmental conditions in 4 classrooms in 6 schools, 3 non-Passivhaus and 3 Passivhaus, 1 1970s, 2 BREEAM schools that we designed ourselves, and 3 Passivhaus schools we designed ourselves. So I'm just going to take you through some of the results of that. First of all, thermal conditions in winter. Why is it important to look at that? Well, we want to make sure they're comfortable, and this has the biggest impact on energy bills. So in terms of our poor old 1970s school, on a Monday morning it's down at 16 degrees, and it hardly rises to 21, which is the minimum you want it to be, really. All week, this is in winter. In our BREEAM school, it's slightly better, though it's slightly chilly every morning. It rises just about. In our first generation Passivhaus school, if anything, perhaps even slightly too warm. And in our second one, we'd learned a few lessons and brought it right down within the parameters of 21 to 23 during the occupied hours of the grey bands on the screen. So really good in winter in terms of thermal comfort. Critical measure of air quality is CO2 levels. It's a very good proxy for air quality. It's really good to demonstrate how well your ventilation is performed. And actually, high CO2 levels really do affect people's ability to concentrate and to learn. So if you can remember back to all those afternoons listening to, you thought they were boring teachers that sent you to sleep. It was probably a combination of boring teachers and really high levels of CO2 that just made you feel really tired. And CO2 has a really big impact. You want to really be below, you should never get above anywhere near 5,000. The average should be below 1,500, and you should be able to reduce it below 1,000 at any point. So in our 1970 school, way up to 5,000, 3, 4, 5,000 quite regularly in winter. And that's because you don't want to open the windows when it's cold outside. In our BREEAM school, some quite high peaks getting up to 2.5, sometimes 3,000 parts per million. In our first Passivhaus school, 1 or 2 peaks just getting to 1,500, but the average well down at 1,000. In our most recent Passivhaus school, right down, averaging below 1,000. So really, really good demonstration of CO2 levels. And this is just looking at looking at one typical day, the black line being the 1970s, the purpley blue line being the pre-Passivhaus, and the yellow line being the Passivhaus. You can see over the school day how the levels are so much better with the constant supply of fresh air into the classrooms. And that's plotting the same things in June, October and December, the average, the spread and the peaks, and you can see again how different they are. Then thermal conditions in summer, really, really important that we're not creating buildings which are also going to overheat because they're so well insulated or have too much solar gain. Now, interestingly, this is our 1970s school, getting up to quite high temperatures, but not over the limits that exist in the school's regulations. This is our BREEAM school. This was our first Passivhaus school, and this is our most recent Passivhaus school, where we're really getting not only the winter conditions, but summer conditions. We're keeping really, really good control of the temperatures. So never even getting above 23, 24 degrees, nowhere near the limit of 25, 5% of 25, which is what Passivhaus sets, or 32, which is what the school regulations set. And then same in summer, just looking at air quality, you expect it to be better in summer because people do have windows open. So 1970s, our BREEAM school and our Passivhaus school, really, really very, very low levels of CO2. Now, the important thing then, as well as the comfort, is to look at how that's doing in terms of energy. So these are CIBSE, typical good practice and median guide for thermal energy in schools. This is the thermal energy in our BREEAM schools, and this is the thermal energy in our Passivhaus schools. So our most recent school is achieving a 90% reduction on TM46, the CIBSE median. So not only are we getting better comfort, we're getting massive reductions in thermal energy. When you add electricity to that, overall we're still getting a reduction of 70%. So really big impact. So I know the main focus today is about retrofit, so I thought I should basically have a quick inclusion of a retrofit project. This is a large house near Oxford where we're retrofitting it to the MEP standard, which is the Passivhaus standard for renovation. So the standard goes from 15 kilowatt hours to 25, and the air changes from 0.6 to 1. So apart from that, very, very similar level, but it just recognises it's much, much harder to do on a retrofit. There's some real challenges and constraints when you're working with existing sites. There's lots of unknowns who you strip out. It's harder to do air tightness. It's much harder to get rid of the thermal bridges because the structure's already there. You have to look very carefully at increasing the insulation to get your energy down and not affecting the hygrothermic properties of the existing structure. So it's really, really sort of more, I think it's more challenging, but it is still very, very doable. So it's quite a large house, 550 square meters. We looked at a whole series of different, including extension, whole series of different interventions. When we first analysed it, the existing house had an annual heat demand of 260 or so kilowatt hour square metre per year. So that equates to something, I think, about £4,000 or £5,000 worth of year in terms of heat. I mean, really, really big levels of heat. So we looked at a series of different scenarios, A, B, C, D, E, and F, to different levels of intervention, right down to NFIT standard. And you can see gradually getting down to a 90% reduction in energy. And this is what we got the heat demand down to between 11 and 21, depending on a few parameters. So from 260 down to, say, 20 is, again, over a 90% reduction in energy. So we have to look very, very carefully at where we're externally insulating the walls, and then how we get the insulation around the roof and insulate inside the roof. So there's some quite tricky things to do there. When you start stripping out, you discover all sorts of odd bits of structure you didn't expect that you have to reassess how to do that with. Looking at how to create air tightness, where the existing joists go into the wall. But it's all doable. It just takes a lot of care and attention. And then things that you never expect, floor which we thought was solid turned out to be just timber with rubble in it. We turned that into an opportunity because we stripped it right out and replaced it with an insulated concrete floor. Lino, which turned out to have asbestos in it. So all sorts of challenges, but it's really is it's hard, but it's still doable. So these are other projects that we're not involved in as architects, just to give you an idea about some of the retrofit that's going on at the moment. So this is a big scheme in Manchester of existing buildings being retrofitted. This is a big project, Wilmcote House down in Portsmouth with the City Council there, 107 units of existing concrete council flats which are being completely externally insulated and retrofitted to NFIT. Project up in Glasgow for a housing association, over 300 houses. In some ways, these sort of projects are easier than a sort of one-off house because you've got a lot of flats in one very, very simple building fabric, but other challenges in terms of concrete structures to deal with. And then there are quite a few examples developing now of existing buildings, domestic buildings being done by different people around the UK. And Warm, who are one of the certifiers, bought a little corner shop with an office above it and retrofitted that to NFIT standard, and is performing very well. So I hope I've showed you that Passivhaus is just very, very simple logic. It's very, very doable. I think somebody once said to me at a talk I did was, it's such common sense, why isn't it more common? And it's a very good question. I think it's really because it's just it requires a sea change in approach, a mindset amongst designers, amongst contractors, to actually take on board doing things differently and to a higher standard. But I thought it would be a nice thing to do to show you in a few lessons. So use PHP as a design tool from day one. I think it's important, particularly on your first project, to work with people who've done Passivhaus before. We did that when we started working with people from Germany. There's more people in the UK now. You need to work collaboratively. I think a constant focus on simplicity of design and detailing, focus workshops with key subcontractors, everyone's working together, better site inspections, and it really is possible. So in the past, buildings were pretty simple, but they were energy consuming and very, very uncomfortable. Presently, we've got into a mode of making buildings very, very complex based on energy offsetting, and ultimately that is, I think, unsustainable. I'd argue for a future in which buildings are, again, simpler, but at the same time, energy saving and more comfortable. And with one of our schools, we've been working with some of the children to create a video which explains what Passivhaus is. So I thought it'd be a nice way to finish my talk just to play you this video in the words of children, describe what Passivhaus is. So I'm hoping this will work.
This is our school.
It might look like any other school, but it has a secret. It's a passive house.
A what?
Passive house.
But this isn't a house.
No.
And it's not very passive either.
I think we might need to explain. Come with us.
This is one of the architects of our school.
A passive house is really just a building that has been built better. While many buildings are drafty and inefficient, a passive house not only uses less energy, it doesn't waste energy. And that means it saves the environment, it saves money, and it's actually more comfortable to be in.
And at a time when climate change is a growing problem, building to passive house standards will reduce CO2 emissions, and clearly that's a good thing.
You're probably wondering how it all works.
We'll show you. Both of these keep your coffee warm, but there's a difference.
Here, the energy is continually put in. The heat goes in and the heat escapes. So more heat goes in, but the heat just escapes, and so on. The heat leaks from the top, the sides, and even all around the bottom. But the thermos is built differently. It is so well insulated, you just heat the water once, pour the hot coffee in, screw the lid on, and it stays warm for hours.
So a bit like that, our school has been made so that it is very well insulated and extremely airtight.
But if it's airtight, how do we breathe?
We know someone who can tell you.
By airtight, we mean that no air is leaking out or getting in where it shouldn't be, which is essentially the case with all other types of buildings. But we do have a mechanical ventilation system, and this allows fresh air into the building and then allows it to circulate efficiently.
And insulated like a normal building?
Our school is actually super insulated with around 300 millimetres of warm cell. That's recycled newspaper. It's like a nice cosy duvet around the building. The floor, the roof, the walls, the windows and the doors, they are all designed so no heat can escape unless we want it to.
So what's putting the heat into the school?
Well, a lot of it comes from us. We're heating the air, and that with the insulation and air control means we only need a little boiler to heat this whole school.
The school is also oriented and designed carefully. It makes use of free heat from the sun in the winter months when the sun is low, but it also stops the sun getting in the summer months when the sun is high.
The air is much refresher too because of the MVHR.
I'm sorry?
Mechanical ventilation with heat recovery.
That's what we were talking about earlier. It lets the fresh air in and the stale air out, without losing the heat.
And fresher air means fresher minds.
We all work better when there's less CO2 in the air.
painting this building is as easy as 1, 2, 3.
You shouldn't really need to touch anything apart from the windows and the thermostat. And even then, not very often.
Let's start with the winter.
Each classroom has windows and ventilation panels. Windows can generally stay closed in the winter as enough fresh air is supplied mechanically, and by keeping the windows closed, we save on energy for heating.
This doesn't mean you can't open windows.
You just shouldn't need to do it often.
So if it gets too hot, adjust the thermostat first.
And if you find you're adjusting things regularly, then contact the facilities manager.
So when it is child's play, told you, next summer.
When it gets too hot, you can open windows and ventilation panels.
So cooler air is entering through these, while fresh air is still being supplied mechanically to the classrooms through the ventilation grills.
Also, in summer, you can turn the lights in the room off, open the blinds and make the most of the daylight. Which reminds me.
So, our building's doing its best to save us energy, but we need to do our bit too. Always think, should it be on? And if not, turn it off.
Things like lights, projectors, screens and computers, they all waste energy if not being used.
We're proud of our school.
I can see why.